If we have a region in space, there's two ways that we can specify it, either via an implicit description or via a parametric description. So an implicit description is an equation that the points of our region need to solve, so or needs to hold for the points of our region. So, for example, an implicit description of a circle of radius a is x squared plus y squared equals a squared. So a point in the plane with coordinates x, y is in the circle if and only if this equation is valid. Whereas a parametric equation is a function whose range is the surface we're interested in. So x equals f t, y equals gt, z equals ht. This is for a curve in 3D space. So a parametrization of this circle would be r of theta is a cos theta, a sine theta for theta between 0 and 2 pi. And both of these types of a description are valuable. So an implicit equation makes it easy to check if a given point is in our region. Whereas for a parametric description, in order to, if we wanted to know, like, is a given point x comma y in our region, we would have to solve a system of equations, x equals a cos theta, y equals a sine theta. Whereas for an implicit description, we can just plug it into here and see if the equation is valid. On the other hand, with a parametric description, it's easy to produce examples of points. So easy to check if a given point P is in S, whereas a parametric description is explicitly telling us how to produce examples of points on here. Again, in order to produce examples from an implicit description, we need to somehow solve for x and y here. So both forms have their advantages. If we're able to isolate one of the variables, then we can get the best of both worlds. We call that an explicit description. So an explicit description is like y equals f of x, or z equals f of xy. And here, this makes it easy to both produce examples of points on the surface and to check if a given point is on it. So you can think of a graph of a function like this. You can think of this as an implicit function by writing it as z minus f of xy equals 0. But you can also think of it as x, you write the parameters x equals u, y equals v, and then z equals f of uv. So you can think of this as a parametric description where the parameters are just the other two independent variables. So it's not always possible to give an explicit description of a region. For instance, if we're looking at a circle like before, this doesn't pass the I guess we call it the vertical line test. So this is not the graph of a function because we have 2 points with the same x coordinate, but different y coordinates. So you can think of the concept of solving equations. So if we think math is about solving equations, in a very general sense, is about going from an implicit description of a region to a parametric description of a region. So there's a kind of duality between these two. So let me explain this. So roughly speaking, k equations in n variables will determine an n minus k dimensional shape. So the idea here is that each equation, so we sort of start out with n dimensions, and then each equation is taking away 1 degree of freedom. Whereas a function with with k inputs and n outputs, this will parameterize a k-dimensional shape in n-dimensional space. So we need k to be less than equal n, but aside from that, the dimension of a shape with a parametric description only depends on the number of inputs and not on the number of outputs. So we sort of start out with 0-dimensional, and then each input we add increases the dimension, whereas with an implicit description, we start out with n dimensions, and each equation we add removes a dimension. So I said roughly because this isn't always true. For instance, if I took z equals x squared plus y squared, this determines a surface in 3D space. But if I just wrote the same equation a second time, now I have 2 equations, but of course I haven't reduced the dimension. This is the same shape. So the equations need to be independent or non-redundant in a certain sense. This can be measured by the Jacobian, so we'll discuss exactly the condition once we get to it. But so for the cases we're interested in, it'll look like this. So if we have implicit versus parametric descriptions. So if we have a curve in 2D space, an implicit description of that will look like f x comma y is 0, whereas a parametric description will be r of t equals x of ti plus y of t j. So notice we only need, here we have 1 constraint and here we have 1 parameter. But if we're looking at a curve in 3D space, or if we're looking at a surface in 3D space, so a surface in 3D space we can specify by one constraint. So maybe let me write the number of constraints versus the number of parameters here. But to describe a curve, we'll need two constraints. So this will give us a surface, and now we need to add a second one to cut down to a curve. So here we have two constraints. A curve in 3D space, we can again parameterize just with one parameter t. Just now we have a third output, z of t k. So this is one parameter. But for a parametric surface, we need two parameters, so two dimensions. Now this will have the form f of uv I plus g of uv j plus h of uv k. Now we have two parameters, u and v. I guess I could call these x, y, and z instead of f, g, and h. But sometimes it's helpful to write functions for them. Okay, so we've sort of seen all of these cases already, except for the new one is surfaces in 3D. So that is the subject of this unit. So let me introduce some terminology. So we'll consider functions r uv equals x of uv I plus y of uvj plus z of uv k for uv contained in some region r in the uv plane. And typically we'll want this to be a closed and bounded region. And in fact, we'll most of the time want R to just be a rectangle. So we'll take U to be between some points A and B, and V to be between some points C and D. And we won't always use the letters A, U, and V for these. Depending on the situation, it might make more sense to call these like theta and phi, for instance, if we were doing something with angles. So R is called the parameter domain, and we'll assume that R is 1-to-1 on the interior of R. So if we have two different points in the interior of R, they can never go to the same output, but we're allowed to. We relax that on the boundary. So we'll see some examples of when on the boundary of R we have 2 points, 2 different points going to the same point. Okay, so now let's see some examples.